All right, folks, welcome to the lecture over 2.4, Complex Numbers. I don't have anybody in the room with me this morning, so I'll just go ahead and get moving forward. Okay, so at the very beginning of this section, you're reminded that mathematics just builds on top of itself. That's why, if you don't understand A or B about mathematics, there's no sense in you moving forward to C. It's just, it builds on top of itself and complements itself. So negative integers, for example, fill a void that's left by the set of positive integers. There's a set of rational numbers and irrational numbers. Not surprisingly, there is a void left by the set of real numbers. And this is very exemplary of our dualistic reality that we live in. You have the extremes, and then somewhere in between you have a balance of those. All right, so the void that is filled by the real or that the real numbers leaves is filled with imaginary numbers. And when we have an imaginary number that also has a real part to it, we call it a complex number. So let me just get my pen going here. We call those complex numbers. So that's what this section is about, is understanding, okay, what's an imaginary number to begin with, and then what's a complex number and how do we work with it. So we know how to find the square root of any positive real number. So if I have, for example, the square root of 16, this is a question asking, what can I multiply by itself to make 16? And that answer is 4. 4 times 4 is 16. We could also do negative 4 times negative 4, but the way I have that written, it's only asking for the principal square root. If I wanted the negative value of that, I'd say, what is the negative square root of 16? And that's negative 4. Either way, it's always asking, what can I multiply by itself to make this particular number underneath, which is called the radicand. So in the study of electricity, the square roots of negative numbers started showing up. And so we had to, as mathematicians, had to answer that with, what the heck is the square root of negative 1? And so let me just remind you that that's asking you the question, what can I multiply by itself to make negative 1? Well, if you think long and hard about that, there's no real number. Negative 1 times negative 1 is positive 1. 1 times 1 is 1. So there's no real number that you can multiply by itself to make negative 1. So we define the value that you can multiply by itself to make negative 1 as I, which means that I squared is the same thing as squaring the square root of negative 1. When you square a square root, it goes away and you're just left with what's underneath. In that case is negative 1. So I squared is the actual real value, negative 1. So this next thing we're looking at is just an example of how to work with the square root of negative numbers. And I do mine the opposite way that they do. I always pull the negative 1 out front. But my advice is to always break off the square root of negative 1. So you see this example here, the square root of negative 49. They are using the product property of roots that says the nth root of a times b is the same thing as the nth root of a times the nth root of b. So in this case, it's a square root, and they've just split negative 49 into 49 and negative 1. Well, we know the square root of 49 can be taken and give an integer, and gives us an integer answer that's considered a perfect square. So the square root of 49 is 7. The square root of negative 1 is I. We call this 7i. Let me just do another quick example here. Let's say we have, what is the square root of negative, let's see, 24. I want something that's not a perfect square. So what I want to do is, of course, break this down into the square root of, I always want to pull off that negative 1 so that all I'm left with is a real number that is positive. And that is times 24, but 24 has a perfect square in it. And we know from, previous studies before this class that you always want to break down into a perfect square and then whatever's left over until you can't do that anymore. So 24 is the same thing as 6, let me write the perfect square first. 4 times 6. 4 being a perfect square, 6 not being a perfect square, and there's no other perfect square factors in 6. So this is as much as this thing can be broken down in regards to trying to find or take the square root of it. So what our square root property tells us is that this is the same thing as the square root of negative 1 times the square root of 4 times the square root of 6. I can now come back and take the roots that I can. Square root of negative 1 is I. Square root of 4 is 2. We write I can't do anything with the square root of 6. We write this as, this is all multiplied, 2 times I times the square root of 6. So notice everything's touching, so that indicates multiplication. 2i square root 6 there. All right, so a complex number is the sum of a real number and an imaginary number. A complex number is expressed in standard form a plus bi, where a is the real part and b is the imaginary part. And it always has to be real plus or minus imaginary. The real comes first, the imaginary comes second. And that's important because in your homework and test, you have to write your answers in standard form, and it must be written this way. So much so that you have your real value, then you have your coefficient if you have one that needs to be written, something besides 1, and then your imaginary unit. Okay, so how do we work with these things? A general note. A complex number is a number in the form of a plus bi. We just saw that. A is the real part, b is the imaginary part. Don't forget, the imaginary number is an even root of a negative number. Given an imaginary number, express it in the standard form of a complex number. So they're just showing you how to rewrite it. So if I have the square root of negative 9, that's the same thing as the square root of negative 1 times the square root of 9. I can come back and take the roots that I can here. Square root of negative 1 is I. Square root of 9 is 3. We write this 3i. All right, next one, square root of negative 24. Oh, I didn't even realize I chose an example on the last page that was going to be an example on the next page. So square root of -1, I want to break this down into something I can take the root of and whatever's left over. We can come back. Square root of -1i, square root of 4, 2. This is 2i. I'm just changing colors here to keep it color-coded. Square root 6. And that's what you end up with. You can't go any lower than either of these. 3i, 2i square root 6. Notice I did not write a real part on here. For example, I did not write 0 plus 3i to separate the real and the imaginary. When you don't have a real part, you don't have to write the 0. It's implied that it's there. Same thing here. This would be 0 plus 2i square root 6. Written out in standard form. Now, if you do have a real part other than 0, then you will need to write it in that form. Okay, so these imaginary or complex numbers rather graph in the complex plane. So if you recall from our study of quadratic functions, we have parabolas that end up with imaginary solutions and don't cross the x-axis where we would expect them to. So that is because imaginary numbers don't graph in the real plane or xy plane that we're used to graphing, and they graph in the complex plane. That's very similar to the Cartesian plane that we're used to. So instead of an x and a y axis, we have a real and we have an imaginary axis. So I have real values. Let's see. I have, say, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6. The imaginary axis looks very similar. So we have I, so it's understood 1i, and then there's 2i, and then there's 3i, 4i, this is really bad with me drawing it, 5i, same thing in the negative direction, that's -i, -2i, -3i, -4i, and so on. I think that's all I need to graph these two. Okay, so if we look at this first example at the bottom, I have a real value, a real unit of 3, and an imaginary unit of -4i. So to graph this, I move out to +3 on the x-axis, and then I'm going to move down 4i. Oops, I didn't put -4i on there. Let me go one more. Oh, I did. It just doesn't look like a 4. That's a 4. There we go. And so down to there, and we end up getting that this right here is a graph of 3 minus 4i. Just that single point. It's just a point living in that complex plane. So let's look at the next one. -4, so I'm going to travel out to -4 on the real axis. And in this case, I'm traveling down I. That's just that first one. And in the complex plane, that puts me about right here. All right. So we can add, subtract, multiply, and divide complex numbers. And you'll be pleased to know that if you can add, subtract, and multiply polynomials, specifically binomials, then you're going to already know how to add, subtract, and multiply complex numbers. So if you look at this first set of information, I have a plus bi, there's one complex number, plus, so I'm adding, c plus di. Notice all you do here is add your real parts and add your imaginary parts, just like you would if you had x's, like real. Let's look at an example. Let's say we have 3 plus 2x plus negative 5 minus 7x. I would combine my integers, and then I would combine my x terms to leave me with 3 and negative 5 make negative 2, and 2x and negative 7x leave me with negative 5x's. So it's the same idea here. And then subtracting, you know, we never subtract polynomials, we add the opposite polynomial. So you have to actually distribute that negative to the terms, and then combine. All right, so let's take a look at a couple of these. This first one here, we have 3 minus 4i plus 2 plus 5i. So I'm just going to point this out for understanding purposes. There's an understood 1 and an understood 1 that gets distributed. So what I can actually do, since 1 multiplying by 1 doesn't change anything, I really don't need my parentheses here. So 3, negative 4i, positive 2, and positive 5i. And now I'm ready to identify and combine my reals and identify and combine my imaginaries. And this ends up giving me 3 and 2 make 5. There's my real. Remember, I have to write my answer A plus or minus BI. It's either A plus or minus BI. And then negative 4i and positive 5i leave me with positive understood 1i. That is in standard form there. Real plus or minus imaginary. Let's look at this next one. We have negative 5 plus 7i minus negative 11 plus 2i. Once again, here we have a positive 1 that's going to get distributed. Here we have a negative 1 that's going to get distributed. It's very important that you pay close attention to what operation is being performed. This is negative 5 plus 7i, and now I have a positive 11 and a negative 2i. Once again, I want to identify and combine my reals first, and then my imaginaries. And I am left with negative 5 and positive 11 is positive 6. Positive 7i and negative 2i is positive 5i. There we go. And here's one given in word form that you have to translate symbolically. So subtract 2 plus 5i from 3 minus 4i. So be very careful about how you set that up. From 1 distributes, negative 1 distributes, and we end up with 3, negative 4i, negative 2, and negative 5i. Identify and combine, real and imaginary. And what I end up with here is 1, 3, and negative 2 make 1. Negative 4i, negative 5i make negative 9i. Real plus or minus imaginary. So that is in standard form there. All right, moving forward. And multiplying. Same as multiplying polynomials, just like the addition and subtraction, except what you have to watch out for is if you multiply I times I, that's I squared. Well, we learned a moment ago that I squared is actually negative 1, because I is equal to the square root of negative 1. And remember, I squared is the same thing as squaring the square root, which leaves me negative 1. So you never want to leave I squared, or actually you never want to leave I raised to any power besides 1 in your final answers. And we'll talk a little bit more about that statement here at the bottom of this slide. Okay, so find the product. So I'm just going to distribute here. And I have 4 times 2, which is 8. Almost said 16 there. And 4 times 5i leaves me with positive 20i. I'm already in standard form, a plus or minus bi. So that's my answer there. All right. And also need to distribute here 1/2 times 5 and 1/2 times negative 2i. Just to give you a refresher on multiplying fractions, that 5 is understood to be over a 1. Whenever I'm dealing with fractions, I like everything to look fraction-y. Same thing with my imaginary unit. You multiply fractions straight across. So numerator multiplies with numerator, denominator with denominator. So this is 5 halves. Do not change this to 2 1/2. The only time you ever want to convert to a mixed number is if you're graphing, or if it's a word problem where it only makes sense to talk about it as a mixed number. Other than that, leave your answers as improper fractions in a simplified form. They're easier to work with, and that's what WebAssign wants, and that's what I want. All right, so this imaginary term, 1 times negative 2i, so it's a positive times a negative, so it's going to be a negative. That's just 2i, and then 2 times 1 is 2. Well, I can come back and divide 2 by 2, and my final answer here is 5 halves minus I, real plus or minus imaginary. Okay, so let's look at this phenomenon of I. This is pretty interesting here, at least in my nerdy world. This is pretty interesting. So we have I, and we've defined I as the square root of negative 1, and we just call that I. We've already looked at I squared. I squared is the square root of negative 1 squared, which gives us negative 1. Now, I cubed is the same thing as I times I squared. That's 3 i's there. So, I is just I squared is negative 1, so that's I times negative 1. We call this negative I to the 4th is the same thing as I squared times I squared. I squared is negative 1. I squared is negative 1. We call that 1. Okay, I'm going to come back, and I'm going to box these in to point them out to you, because here's where it gets cool. So let's look at I to the 5th. I to the 5th is the same thing as I to the 4th times I. Well, we know from the last column that I to the 4th is just 1. I is just I. This gives me I. I to the 6th is I to the 4th times I squared. I to the 4th is 1. I squared is -1, which gives -1. I to the 7th is I 4th times I cubed. I to the 4th is 1. I cubed is -I. 1 times -I is -I. I to the 8th is I to the 4th times I to the 4th, which is 1 times 1, which is 1. Okay, let me just box these in. Hopefully you're already catching on here. Let's look at this last column. I to the 9th is the same thing as I to the 4th times I to the 4th times I, which is 1 times 1 times I, which is just I. I to the 10th is I to the 4th times I to the 4th times I squared, which is 1 times 1 times -1, which is -1. I to the 11th is I to the 4th times I to the 4th times I cubed, which is 1 times 1 times -I, or -I. I to the 12th is I to the 4th times I to the 4th times I to the 4th, 1 times 1 times 1, which is 1. So hopefully by now you've picked up on the fact that this just continues through infinity in these cycles of 4. So that's why a moment ago I said you can never leave an imaginary number raised to any power other than 1, because you can always break it down to either I, the real number -1, -I, or the real number 1. And you can see it happens in cycles of 4. So let me pull out one of these and show you something. We'll look at I to the 9th. Since I know these come in cycles of 4, if I divide 9 by 4, it doesn't really matter how many times it goes in. It matters about the remainder. 4 goes into 9 twice. 2 times 4 is 8. Here's a blast from the past. Remainder of 1. That remainder points you to which level of the cycle of I this is going to take you to. So let me just point this out to you real quick. If you have a remainder of 1, we already know that this is equal to I. I mean, that's what we figured out up at top. I to the 9th is I. So if you have a remainder of 1, it will always correspond to I. A remainder of 2 will always correspond to -1. Remainder 3 will correspond to -I. And about to trick you, no remainder corresponds to +1. So for example, if I was thinking about I to the 8th, what the heck is I to the 8th? Well, since it comes in cycles of 4, I divide 8 by 4. That's 2. There's no remainder there, so that's going to tell me that I to the 8th is equal to 1. So my question now is, what is I to the 37th? Well, there's no need for you to sit here and go through these cycles until you hit 37, because we know that they come in cycles of 4s. So all I do is divide 37 by 4. So 4 goes into 37 9 times. 9 times 4 is 36. Here's the important part. I have a remainder of 1. So without even having to go through all those cycles, as long as I know this remainder, I now know that I to the 37th is equal to I because it has a remainder of 1. It's going to be at the top of that next cycle. Pretty interesting, huh? Okay, so practice with multiplying imaginary or rather complex numbers. So you're going to do the same type of distribution that you do with polynomials. 4 times 2, 4 times -5, 3i times 2, and 3i times -5i. Okay, so I have here 4 times 2 is 8. 4 times -5i is -20i. 3i times 2 is positive 6i. And 3i times -5i is -15i squared. Well, I just learned that I can replace I squared with -1. So that's really -15 times -1. I also have imaginary units in the center that I can combine. So this is 8. -20i and 6i give me -14i, and -15 times -1 is positive 15. My final answer written in standard complex form, 8 and 15, that real value needs to go first. That's 23 minus 14i. And that is in complex form, real plus or minus, coefficient, imaginary. Okay, same thing here. Just going to distribute like I normally would. 3 times 2 is 6. 3 times 3i is positive 9i. -4i times 2 is -8i. And -4i times positive 3i is -12i squared. Before I do anything, I come back and remind myself, well, I squared is just -1. And now I'm ready to combine my reals and my imaginaries. So 6, this is positive understood 1i, and then I have plus 12. Adding my reals, 18 plus I is what I end up with. Okay, let's take a look at this last one, because this is another interesting thing. 4 times 4, 4 times 2i, -2i times 4, and -2i times 2. Notice I have the same values sitting in the real position. I have the same imaginary units. The only difference between these two complex numbers is one of them is subtraction and one of them is addition. So you should know from past experience that these are conjugates of each other. Whenever you have the same first value and the same second value, but you have one that's added and one that's subtracted, those are called conjugates of each other. Watch what happens when you multiply complex conjugates. And this is really important. 4 times 4 is 16. 4 times 2i is positive 8i. -2i times 4 is -8i. And -2i times 2i is -4i squared. Once again, before we do anything, let's remind ourselves that I squared is really -1. And positive 8i and -8i create a zero pair. So I have 16 plus 4, which is just 20. Notice, I have no imaginary unit left. All I'm left with is a real number. This will always happen when you multiply complex conjugates. Okay, how is this useful to us? Why is this so important? Well, once again, if you dig way back in the depths of your memory, you'll remember that we cannot leave a square root in a denominator. We do what we call rationalize. Uh-oh, I grabbed a white pen and that doesn't help y'all. So let's say we have something like 3 over the square root of 2 plus 4. We can't leave that square root in the denominator. We have to do what we call rationalize. So to rationalize with square roots, we remember that we just multiply by a clever form of 1 in the form of the conjugate. So square root 2 minus 4 over square root 2 minus 4. Now, I'm not changing this expression because the square root of 2 minus 4 divided by the square root of 2 minus 4 is just 1. And multiplying something by 1 does not fundamentally change it. Now we're going to make it look different because we can't have that root in the denominator. But it's not going to change the value of it because I'm just multiplying by 1. So here's what we have to do. We have 3 times square root of 2 minus 4 over square root 2 plus 4 times square root 2 minus 4. Okay, so we have some distribution to do here. I need to distribute here and here. I also need to distribute here, 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 and here. And when I do so, in my numerator, I get 3 square root 2 minus 12 over, okay, square root of 2 times the square root of 2 is the square root of 2 squared. That just leaves me with 2. Square root of 2 times negative 4 is negative 4 square root 2. 4 times the square root of 2 is positive 4 square root 2. And 4 times negative 4 is negative 16. Notice we've created those two middle terms again that are going to drop that root out of the denominator. So what I'm left with is 3 square root 2 minus 12 over 2 minus 16 is negative 14. And to be precise, it's bad form to leave a negative leading term in the denominator, so I would want to bring that negative out front and say this is 3 square root 2 minus 12 over positive 14, just to be in good form. And WebAssign will want good form. Ooh, excuse me, it's early. All right, so I did all that to say, since I is equal to the square root of negative 1, you cannot leave imaginary numbers in your denominator. Just like you can't leave any sort of root living in your denominator. You've got to rationalize it. So the way we do that is by using complex conjugates. Because when we multiply complex conjugates, we always end up with a real number value. So that's how we're going to get those imaginary units out of the denominator. So dividing two complex numbers is more complicated than adding, subtracting, and multiplying them because we cannot divide by an imaginary number. That's what I was just telling you. Meaning that any fraction must have a real number denominator. To write the answer in standard form, A plus BI. We need to find a term by which we can multiply the numerator and the denominator that will eliminate the imaginary portion of the denominator so that we end up with real number as the denominator. This term is called the complex conjugate. So here we have A plus BI, A minus BI. Those middle terms are always going to drop out and leave you with a real number. So let's take a look. The first thing we're doing here is just figuring out, okay, what's the complex conjugate? And like I said, it's always the same A and B's, so the same real term, the same imaginary term, just have opposite signs. So the complex conjugate of 2 plus I square root 5 is 2 minus I square root 5. So no brain science here. Okay, this negative 1/2 I, that's like 0 minus 1/2 I. You're not going to see the 0 up front, so the complex conjugate is just 1/2 I. So that's understood to be 0 plus 1/2 I, complex conjugate. And then finally, negative 3 plus 4I, complex conjugate, negative 3 minus 4I. Okay, now let's use them. All right, so we have the complex value here, negative 5 plus 3I over 2I, and I cannot leave that 2I in the denominator. So what I do is I multiply the numerator and the denominator by a fraction that is the complex conjugate of the denominator. So what I call this is my clever form of 1. And you'll hear me say that a lot. Multiply by your clever form of 1. So here I'm going to multiply by negative 2I, which is the complex conjugate of the denominator, over negative 2I. Once again, that's just 1. So I'm not changing this thing. I'm just making it look different. So here I'm going to pull that negative 2I out front and show that I've got to multiply it by both terms there, negative 5 plus 3I. And in the denominator, I have 2I times negative 2I. All right, so I need to do some distribution in the numerator, here and here. Negative 2I times negative 5 is 10I. And negative 2I times positive 3I is negative 6I squared. And that's divided by 2I times negative 2I is negative 4I squared. So before I go further, I'm going to stop here and say, whoop, I squared is really just negative 1. I squared is really just negative 1. I'm going to write another step just to simplify this. 10I plus 6 over 4. It feels like you should be done, but you are absolutely 100% not done, because this is not in standard form, A plus or minus BI. I have to make it look like that. So the first thing I'm going to do, since I know that my imaginary unit needs to come second, I'm going to flip-flop my numerator terms. 6 plus 10I over 4. And now I need to split that fraction up into its real and its imaginary. So this is the same thing as 6/4 plus 10I over 4. And now I need to come back and simplify my fractions. 2 goes into 4 twice and into 6 3 times. 2 goes into 4 twice and into 10 5 times. So at this point I have 3/2 plus 5I over 2. I still can't leave it like this. I've got to have real plus or minus coefficient and then my I. So my final form is 3/2 plus 5/2 I, A plus BI. So I just pull that imaginary unit off of the fraction. Okay, so this next one's a little trickier. It says to divide 2 plus 5I by 4 minus I. Okay, so I look at my denominator And I see I have an I down there, so I need to multiply by my clever form of 1, which is the complex conjugate of the denominator over the complex conjugate of the denominator. So here's all the work I'm about to have to do. I have 2 plus 5i times 4 plus I divided by 4 minus I times 4 plus I. I come back and I do all my distribution here, 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 and here, here, and here. So 2 times 4 is 8, 2 times I is positive 2i, 5i times 4 is positive 20i, and 5i times I is positive 5i squared. And that's being divided by 4 times 4 is 16, 4 times I is positive 4i, negative I times 4 is negative 4i, and negative I times positive I is negative I squared. Come back and remind yourself those are just negative ones. And I've got opposites there, and I have I terms that I can combine. So I have 8 plus 22i, and then positive 5 times negative 1 is negative 5, over 16, and negative 1 is plus 1. I've got my real numbers in the numerator that I can combine. So this is 3 plus 22i over 17. And now I need to write it in standard form. 3/17 plus 22/17 I. There's my final answer. All right. So these last 4 problems are just practice problems in working with square roots of negative numbers and concepts involving I. Okay. So whenever you have the square root of a negative number, you always want to pull that negative off and simplify that root. So I have the negative square root of negative 4. Well, that's the same thing as negative, and that's really a negative 1 that's being, let me draw this in. It's really a negative 1 that's being multiplied by that square root of negative 4. So I can put that here and say, okay, that's a negative 1 that's being multiplied by the square root of negative 4 is the same thing as the square root of negative 1 times the square root of 4. So there's my first term. And I'm subtracting from that 4 times the square root of negative 1 times the square root of 25. Now I want to come back and take the roots that I can. Square root of negative 1 is I. Square root of 4 is 2. Square root of negative 1 is I. Square root of 25 is 5. Okay, so I'm going to multiply my factors together that form my 2 terms. Negative 1 times I times 2 is negative 2I. And that's subtracting 4 times I times 5, which is negative 20I. I end up with negative 22 I's here. Okay, this next one is a tad bit tricky, but it's not too bad. This particular problem is trying to get you to recognize a pattern that occurs here. So if I have 1 minus I raised to the k power, it says evaluate this for a k of 2, 6, and 10. So for a k of 2, that would be 1 minus I squared. That's the same thing as 1 minus I times 1 minus I. I need to come back and do my distribution. 1 times 1 times negative I times 1, negative I times negative I. And what I get here is 1 negative I, negative I, negative I squared, and come back and say, oh, that's just negative 1. And I can combine my negative i's there. This leaves me with 1 minus 2i plus 1. And, oh, no, I'm sorry. That's plus I squared. Negative I times negative I is positive I squared. So that's actually subtracting a 1 there. Thought there was something going on weird. Okay. So this is actually minus 1. So 1 minus 1 is 0, so I'm just left with negative 2i here. Notice k was 2, and we get negative 2i. Okay, so for a k of 6, what that is the same thing as is 1 minus I squared cubed, because when I raise a power to another power, I multiply. Well, I already know what 1 minus I squared is, so I can just cube that. So this is the same thing as negative 2I cubed. Negative 2 times negative 2 times negative 2 is negative 8. I times I is I cubed. We learned a moment ago that I cubed is the same exact thing as negative I. So this is negative 8 times negative I, which gives me positive 8I. Okay, so I'm just going to point these out. Okay. And then we're asked to do a K of 10. Well, that's going to be the same thing as 1 minus I squared raised to the 5th power, because 2 times 5 is 10. So that's negative 2I to the 5th. Negative 2 times negative 2 times negative 2 times negative 2 times negative 2 is negative 32. I to the 5th. Well, I to the 5th, that's 4 with a remainder 1, so that's just I. So this is negative 32 times I, which is negative 32I. I'm going to come here and I'm going to color code this for you so maybe you can start seeing what's going on. And then it says predict a K of 14. I'm actually going to do 14 and then we'll predict a K of 16. So let's figure out what a K of 14 is. So that's the same thing as 1 minus I squared to the 7th, which is negative 2I to the 7th. 2 to the 7th, I believe is 128, but let me just check. Yep. So that is negative 128. I to the 7th. And I to the 7th, well, when I divide 7 by 4, I get 1 with a remainder of 3. That takes me to negative I. So this is negative 128 times negative I, which is positive 128. I'm sorry. Yeah, 128I. And I'm going to color code this. Okay, and let me point one more thing out. So, and let me also point this out, that this would be to the first and the fifth. So you can see, if you look at the value of k, and you divide that value of k by 2, because we're squaring that thing on the inside, you get 1, 3, 5, 7. So you get the outside power happening. Well, watch this. 2 raised to the first power is 2. This first one's negative. And then all of these are just an imaginary unit. Okay, so this next one, 2 cubed is 8. It's positive. So we're going to toggle between negative and positive. And for this next one, 2 raised to the fifth power, it's going to be a negative one, so negative 32i. 2 raised to the seventh power, it's a positive one, so positive 128. So if I have a k of 18, that's 4 more, that's the same thing as 1 minus I squared to the 9th. I don't need to go through this. 2 to the 9th power, let's see, 2 to the 9th power is 512. I'm toggling to a negative, so negative 512i would be my value there. Hopefully that was clear for you. All right. 2 last problems here. 1 over I plus 4 over I cubed. Okay, so this is going to be helpful for those of you that don't remember how to work with fractions, with adding and subtracting. You have to be able to, you have to get a common denominator to add or subtract fractions. So in this case, I have an I in one denominator and an I squared. So I'm just going to rewrite this. 1 over I plus 4 over I cubed. I cannot put these together because they would both need to be I cubed in the denominator. So what I do is I come back and I multiply by a clever form of 1 that will give me that I cubed in the denominator. So that's I squared over I squared, because I squared times I is I cubed. So now I have I squared over I cubed plus 4 over I cubed. I now have a common denominator. So I am ready to combine my numerators over my common denominator. And that gives me I squared plus 4 over I cubed. Well, I squared, don't forget, is negative 1, and I cubed is negative I. So at this point, here's where I am. This is negative 1 plus 4, which is 3 over negative I. I can't leave that I in the denominator. I've got to rationalize it. So I multiply by my complex conjugate, I over I, and that leaves me with 3I over negative I squared. Well, I squared is just negative 1. That's a negative times a negative 1. So I have 3I over positive 1, which is just 3I. Okay, and this last one says add 3 plus 2i over 2 plus I with 4 plus 3i. So I'll just point out that this 4 plus 3i is over 1. I'm going to rewrite my problem. So I've got room to work. 3 plus 2i over 2 plus I plus 4 plus 3i over 1. Still have to get a common denominator to be able to add these. This thing needs an entire 2 plus I in its denominator to be able to combine those fractions. Okay, so now I have 3 plus 2i over 2 plus I plus, okay, so I've got some multiplication that needs to happen here, 4 plus 3i times 2 plus I over 1 times 2 plus I is just 2 plus I. Okay, I'm going to go ahead, before I combine my numerators over my common denominator, I'm going to go ahead and do my distribution here. And now I have 3 plus 2i over 2 plus I plus, okay, 4 times 2 is 8, 4 times I is positive 4i, 3i times 2 is positive 6i, and 3i times I is positive 3i squared over my now common denominator, 2 plus I. Okay, so I am ready now to combine my numerators over my common denominator. So I have, so far, 3 plus 2i plus 8 plus 4i plus 6i plus 3i squared over my common denominator, 2 plus I. Don't forget, I squared is really just -1. Okay, so I've got I terms that I can combine, and I've got real terms that I can combine in my numerator. Okay, so my reals, 3 and 8 make 11, and then I have a 3 times a -1, which is a -3. So my 3 and my -3 are opposite, so they zero out. So I'm just left with a real value, 8, in the numerator. And then I have 2i and 4i, which make 6i, and 6i, and 6i make positive 12i. And that's over 2 plus I. Now that I've added them together, now I'm ready to rationalize. So I come back and multiply by my clever form of 1, which is the complex conjugate of the denominator, 2 minus I over 2 minus I. And that gives me 8 plus 12i times 2 minus I over 2 plus I over 2 minus I. And I've got a lot of distribution to do. Got to do all this too. All right. Thank goodness this is the last problem. This one's a doozy. All right. 8 times 2 is 16. 8 times -I is -8i. 12i times 2 is positive 24i. And 12i times -I is -12i squared. 2i times 2i is 4. 2 times -I is -2i. I times 2 is positive 2i. And I times -I is -I squared. Okay, before I start combining, I'm going to make sure I remember that that I squared is just -1. Same thing here. And I've got opposites there. Got like terms here I can combine. All right. So in my numerator, so far I have 16 plus 16i, because I'm combining my negative 8i with my positive 24i, and that leaves me with positive 16i. And then negative 12 times negative 1 is positive 12 over 4, and that's a minus negative 1, so 4 plus 1 is 5. 16 plus 12 is 28 plus 16i over 5. I cannot leave it like that, though. My standard form answer is 28 fifths plus 16 fifths I. All right, that's all I have for you on complex numbers. I hope this was helpful.